Right now, the ground beneath 28 of America's largest cities is sinking, and a study published in the journal Nature Cities confirmed it. Not as a projection, not as a worst-case scenario, but as a measured, documented fact. Every single one of those 28 cities is going down, and in all of them, at least 20% of the land area is already subsiding. About 33.8 million Americans are living on land that is actively dropping beneath them, and most of them have no idea it is happening. But sinking is only one part of what this video covers. In Arizona, the ground is cracking open. Fissures running 2 miles long, 15 feet wide, 90 feet deep, tearing through neighborhoods and irrigation canals. Across Texas, Kansas, and the Great Plains, the single largest underground water supply in the country is draining faster than it can ever recover. And in the American Southwest, the Colorado River, which delivers water to 40 million people, is at the center of a reckoning that will force some of the most difficult decisions this country has ever made about who gets water and who doesn't. What's causing all of it, who it affects, how bad it already is, and what can realistically be done. That's what this video covers. Start with the ground that's disappearing beneath our cities. 33.8 million people. In May 2025, a research team at Virginia Tech published what may be the most complete study ever conducted on American land subsidence. Graduate student Leonard Ohenhen and Associate Professor Manucha Shirzai led the effort, using satellite radar technology to measure ground movement across the country's 28 biggest cities between 2015 and 2021. What they found was stark. Every city they measured had at least 20% of its land area sinking, and in 25 out of those 28 cities, at least 65% of the land area was going down. Houston ranked as the worst, with 42% of its land subsiding faster than 5 millimeters per year and 12% dropping faster than 10 millimeters annually. Fort Worth, Dallas, New York, and Chicago all registered more than 2 millimeters of sinkage per year across large portions of their land. Columbus, Seattle, Detroit, Denver, Charlotte, Washington, D.C., San Antonio, San Diego, Nashville, Los Angeles, and Las Vegas all clocked between 1 and 2 millimeters of annual loss. Cities like Boston, Phoenix, and Austin measured below 1 millimeter per year, which sounds reassuring until you hear what Ohenhen himself said about cumulative effects. 4 millimeters per year becomes 40 millimeters over 10 years, and so on. That cumulative effect can add up. And when it adds up under roads, rail lines, airport runways, water pipes, and home foundations, the cost becomes very real very fast. Building risk data from the study drives that point home. Across all 28 cities, more than 29,000 buildings sit in high or very high damage risk zones. And the city with the worst structural exposure isn't Houston or New York. San Antonio holds that distinction, with 1 in every 45 buildings in a high-risk damage area. 80% of all urban subsidence in the United States traces back to a single cause: groundwater extraction. Cities pump water out of the ground for drinking, for industry, for agriculture, and in doing so they remove what scientists call pore pressure, the water between sediment and rock that holds it apart. Pull the water out and the spaces collapse. The ground above settles. And here's the part that changes the entire calculation. Once sediment compacts from this process, it doesn't recover. That change is permanent. Building weight physically compresses soil on top of whatever groundwater extraction is doing below. Oil and gas removal pulls additional material from underground. Tectonic processes and the long, slow rebound of the Earth after the last ice age contribute as well. But groundwater pumping drives roughly 80% of the total, according to the Virginia Tech research, which makes it both the dominant cause and, at least theoretically, the most controllable one. Research from UC Riverside economist Mehdi Nemeti put a price tag on what homeowners actually lose. Subsidence-related problems cost American homeowners an average of 6% of their home value, and in areas with heavy subsidence, that figure climbs to 8.1%. Standard homeowners insurance in most states covers none of it. A cracked foundation from compacting soil underneath is the homeowner's problem alone. Now take those numbers into the cities where this process has been running the longest, and where its consequences have already reshaped the physical landscape. Starting with the city that became the defining case study for what happens when a major American metro pumps too much water out of the ground. Houston has been sinking faster than almost any major city in the developed world, and it has been doing so for decades, not years. Between 1943 and 1973, roughly 4,700 square miles of land southeast of downtown sank by at least 6 inches, an area comparable in size to Connecticut. Near the Houston Ship Channel, where the sinking concentrated most severely, the land dropped 9 feet. By 1979, some parts of the Houston-Galveston region had subsided by as much as 10 feet total, and since Houston was founded in 1836, groundwater withdrawal has caused about 3,200 square miles of land to sink more than a foot, with some locations losing 12 to 13 feet of elevation permanently. To understand what those numbers mean in practice, you need to know about Brownwood. It was a neighborhood near the Ship Channel, and it sank so gradually that many residents didn't fully grasp what was happening until their homes started flooding on a regular basis. Some structures got swallowed by the bay. When Hurricane Alicia came through in 1983, the remaining buildings were declared uninhabitable. The neighborhood was abandoned, and what had once been a residential community now sits largely underwater. Brownwood is gone. Not damaged, gone. The aquifer damage in the Houston-Galveston area is almost too large to process in familiar terms. Subsidence across approximately 12,000 square kilometers, covering nearly all of Harris and Galveston counties, permanently destroyed 12 cubic kilometers of groundwater storage capacity, which equals 60 times the volume of Lake Houston, or about 8 years worth of water usage for both counties combined at 2023 consumption rates. That capacity isn't recoverable. The space where the water used to be held no longer exists. What makes Houston's story even more unsettling is that subsidence there doesn't just flood neighborhoods. It activates geological faults. Since the late 1930s, 86 active faults in the Houston area have offset the land surface and caused damage to buildings and highways across the metro. As Earth compacts unevenly, it stresses fault lines that were previously dormant, and researchers at the University of Houston have warned that continued pumping in areas like Katy and the Woodlands, two of the region's fastest-growing suburbs, will likely reactivate those faults and increase their activity over time. The 2017 Hurricane Harvey flooding wasn't just a weather event either. Research published after the storm found that groundwater pumping and oil and gas extraction had caused land subsidence that directly correlated with how severe the flooding became in specific areas. The land had sunk, the drainage capacity had fallen with it, and when the storm arrived, the water had nowhere to go. Subsidence didn't cause Harvey, but it made Harvey worse. Texas eventually acted. In 1975, the 64th Texas legislature created the Harris-Galveston Subsidence District, the first regulatory body of its kind in the United States, which began requiring a shift from groundwater to surface water throughout the region. That decision has measurably slowed the sinking, but slowing subsidence and reversing it are completely different things. As University of Houston geologist Shuhab Khan has put it, once groundwater is depleted and land subsides, it cannot realistically be reversed. Houston protected itself from further catastrophic loss, and it cannot undo what already happened. Brownwood remains underwater. The 12 cubic kilometers of storage capacity remain gone. What Houston bought with regulation was a future less bad than the one it was heading toward, and that distinction matters enormously as the same process plays out in 27 other American cities. When your flood protection is sinking too, where Houston is the story of a city that started sinking and eventually slowed the process. New Orleans is the story of a city that kept sinking and then built its entire survival strategy on top of ground that was still going down. Much of the New Orleans area currently sits 1.5 to 3 meters, roughly 5 to 10 feet, below mean sea level, according to U.S. Geological Survey data, with ground in the area dropping at about 1 centimeter per year. By the time Hurricane Katrina came ashore in August 2005, parts of the city had already reached 5 meters, more than 16 feet, below sea level, which helps explain why the flooding was so catastrophic. After Katrina killed more than 1,800 people, the federal government spent $15 billion constructing what was supposed to be a protective flood control system for New Orleans. Levees, flood walls, and storm gates built to shield the city from future storms. And here is where the story turns especially grim. Research published by Tulane University in 2025 revealed that the $15 billion system itself is sinking, with parts of it dropping at up to 28 millimeters per year. Some neighborhoods, wetlands, and stretches of floodwall are losing more than an inch of elevation every year. The area around Louis Armstrong International Airport, where recent construction has concentrated, registers 27 millimeters of annual loss. In certain locations, the ground is dropping nearly 2 inches per year. A flood control system works by maintaining a height advantage over the water it's meant to hold back. Engineers build in margins of safety, calculating what the levee needs to be to handle a storm of a given size. But when the levee itself sinks, even slowly, even a few millimeters at a time, that safety margin erodes without a single storm touching it. Professor Mead Allison of Tulane, a co-author of the study, framed it plainly. These results are a wake-up call. We need ongoing monitoring and maintenance to ensure that our flood defenses don't lose their level of protection beneath us. Projecting forward makes the picture harder still. Taking both the current subsidence rate and mid-range estimates of sea level rise over the next century into account, the parts of New Orleans that sit 1.5 to 3 meters below sea level today will likely be 2.5 to 4 meters or more below sea level by 2100. The city isn't managing a static problem. It's managing one that compounds. There is, buried in the New Orleans data, one genuinely encouraging finding. Land in the Michoud neighborhood rose by up to 6 millimeters per year between 2016 and 2020, and the reason matters. A local power plant had been extracting groundwater in the area for years, and when the plant was decommissioned in 2016 and the pumping stopped, the water table began recovering and the land followed. Recovery was partial and localized, not a full reversal of decades of damage. But it demonstrated that the process is not completely one-directional, and for cities trying to figure out where to intervene first, that's a meaningful piece of evidence. Houston and New Orleans tend to dominate the conversation about sinking American cities, but a study published in January 2024 in the journal PNAS Nexus, again from the Virginia Tech team of Ohenhin and Sherzay, found that the entire U.S. East Coast is sinking, and in some stretches, sinking faster than sea levels are rising. Large areas of the East Coast register subsidence of at least 2 millimeters per year, and several stretches of the mid-Atlantic coast, covering more than 1,400 square miles, drop faster than 5 millimeters annually, which exceeds the current global average rate of sea level rise at 4 millimeters per year. More than 2 million people and 800,000 properties fall within those affected zones, and the sinking doesn't happen in empty fields. JFK International Airport and LaGuardia Airport, both of them, runways included, subside at rates exceeding 2 millimeters per year. LaGuardia had just completed an $8 billion renovation and earned the ranking of best airport in the United States from Forbes Travel Guide in 2024. And none of that changes the fact that it sits on ground that is actively going down. New York's railway systems share the same situation. All that infrastructure, all that investment on subsiding ground. Charleston, South Carolina presents another striking data point. A coastal city of about 800,000 people, Charleston sinks at roughly 4 millimeters per year, making it one of the fastest declining cities on the eastern seaboard, with researchers tracing part of that loss to groundwater pumping. One of the counterintuitive findings from the East Coast research involves the comparison with the West Coast. The Pacific Coast has a reputation for geological instability, earthquakes, volcanic activity, the San Andreas Fault. Yet when it comes to the specific problem of sinking land interacting with rising seas, the Atlantic coast is in worse shape. As Professor Sherzay stated directly, subsidence on the Atlantic coast is actually worse than on the Pacific coast. It is more widespread, more rapid, and more impactful because communities and infrastructure are located closer to sea level than on the West Coast. East Coast communities have less elevation buffer, which means the same rate of sinking carries heavier consequences. Ohenhin's warning on this issue names something beyond just the physical problem. Continuous unmitigated subsidence on the U.S. East Coast should cause concern. This is particularly in areas with a high population and property density and a historical complacency toward infrastructure maintenance. That phrase, historical complacency toward infrastructure maintenance, describes not just how structures age but how institutions respond. Subsidence doesn't trigger emergency declarations. It doesn't make the evening news. A crack forms, a pipe shifts, a rail line needs realignment, and the connection to decades of slow ground movement gets lost in the maintenance budget. The damage accumulates long before anyone asks why. underground, in millimeters, measurable only by satellite. In Arizona, groundwater depletion takes a different and far more visible physical form. The ground doesn't just sink, cracks. Earth fissures are pervasive cracks that form on valley floors when land subsides unevenly, and they are a direct product of excessive groundwater withdrawal. These are not hairline fractures. Some run 2 miles long, stretch 15 to 25 feet wide, and plunge 90 feet deep, with researchers believing they extend all the way down to the top of the water table, which in some parts of Arizona sits several hundred feet below the surface. More than 3,000 square miles of Arizona, including expanding areas around Phoenix and Tucson, now show the effects of ground subsidence and fissuring from this cause. The first fissure attributed to excessive groundwater withdrawal appeared near Picacho in the early 1950s. Since the 1940s, water level declines exceeding 150 meters in certain areas drove land subsidence of more than 5.7 meters in both western metropolitan Phoenix and Eloy. The scale of the problem has grown steadily ever since. Putting a dollar figure on fissure damage is difficult, but specific incidents reveal the scale. Repairs to a single irrigation canal near Scottsdale Air Park in 2007 ran an estimated $820,000. One canal, one incident. The annual statewide cost is believed to reach into the millions, which many analysts consider a conservative figure given how much damage goes uncounted. The worst active hotspot right now is the Wilcox Basin, about an hour east of Tucson. Large-scale agricultural pumping has driven dramatic consequences there. A 5-year study from 2017 to 2021 found some areas sinking at rates of up to 6 inches per year, with nearly 3 feet of total loss over the study period. Since the 1950s, portions of the Wilcox Basin have sunk as much as 12 feet. One specific area northwest of town has dropped nearly 11.6 feet since 1969, and at current rates, researchers estimate the total could eventually reach 30 feet, comparable to the worst losses already recorded in California's Central Valley. Driving much of the Wilcox problem isn't municipal use but agricultural production, specifically large-scale operations. Some of them foreign-owned, pumping massive volumes of groundwater to grow alfalfa for export. Alfalfa is among the most water-intensive crops grown in the American Southwest, and the idea that irreplaceable, ancient groundwater is being mined from desert aquifers to produce an export crop has become one of the sharper fault lines in Arizona's water debate. In 2025, Arizona designated the Wilcox Basin as a new active management area, giving regulators the authority to restrict groundwater withdrawals there for the first time. Whether that designation arrives in time to prevent further irreversible damage remains an open question. And the harder truth, as geophysicist Brian Conway of the Arizona Department of Water Resources has made clear, is that once the sediment compacts, nothing can restore it. Stop the pumping, recharge the aquifer, and the ground still won't rise back up. The fissures won't close. Intervention stops the damage from getting worse. It doesn't undo the damage already done. California's Central Valley produces a remarkable share of the food Americans eat: fruits, vegetables, nuts, dairy, and ranks among the most productive agricultural regions anywhere on Earth. It also ranks among the most severely subsiding regions in the United States. Sinking in the Central Valley began in the 1920s and has continued ever since, with the U.S. Geological Survey estimating that some locations have dropped as much as 28 feet, 8.5 meters, over that period. The USGS called it one of the single largest alterations of the land surface attributed to humankind, which is a statement that deserves a moment to absorb. California's severe drought years from 2012 to 2016 accelerated the problem sharply. Surface water became scarce, farmers turned to groundwater instead, and the pumping intensified dramatically. NASA monitoring during that period found areas subsiding as fast as 2 feet per year. Near Corcoran, the land dropped 13 inches in just 8 months. Parts of the California Aqueduct, one of the most important water delivery systems in the state, lost nearly 13 inches of elevation. A Stanford University study published in November 2024 confirmed that the San Joaquin Valley has sunk at a record pace since 2006, with overpumping causing the land to drop by more than a foot per year in many years. infrastructure losses from all of this sinking are enormous. The Frying-Kern Canal, a critical water delivery artery for the valley, lost 40% of its capacity in some stretches due to subsidence damage. The California Aqueduct lost more than 20% of capacity in affected sections. Repairing just the surface water conveyance infrastructure damaged between 1955 and 1972 cost more than $1.3 billion in 2013 values, and that figure covers only the earliest phase of damage in a process that continued for decades afterward. Corcoran, California tells the human side of this story better than almost anywhere else. The town of roughly 22,000 people, with a median income of about $40,000, has sunk as much as 11.5 feet in some places over the past 14 years, enough to swallow the entire first floor of a two-story house, and at times it ranked as one of the fastest sinking areas in the country. To keep from flooding, the town had to rebuild its levee system at a cost of $10 million, and residents absorbed that cost through property tax increases of roughly $200 per year for 3 years. In a community earning $40,000 a year on average, that's not an abstract number pulled from a budget document. Those are real dollars from real households, paying to fix a problem largely created by large agricultural operations, not the people writing the checks. A UC Riverside study quantified the housing value toll across the wider valley. Homes in subsiding areas lost between 2.4% and 5.8% of their sale value, between roughly $6,700 and $16,000 per home, and in aggregate, the study estimated $1.87 billion in total housing value lost across the Central Valley from subsidence alone. California passed the Sustainable Groundwater Management Act in 2014, requiring critically overdraft basins to reach sustainability by 2040. The path to that goal will almost certainly require reducing irrigated farmland, which is economically painful and politically contentious, and the process has barely begun. Every story covered so far involves a tension between the water people need and the damage from taking too much of it. Houston, New Orleans, the East Coast, Arizona, California, in all of those places, some alternative water sources exist: rivers, surface reservoirs, other aquifers. The Ogallala Aquifer is different because there is no backup. Stretching across 174,000 square miles beneath 8 states: Colorado, Kansas, Nebraska, New Mexico, Oklahoma, South Dakota, Texas, and Wyoming, the Ogallala took millions of years to fill, fed primarily by glacial melt during the last ice age. Today it supports 20% of the nation's wheat, corn, cotton, and cattle production and accounts for 30% of all irrigation water used in the United States, pumped by nearly 200,000 irrigation wells, most of them sunk since the 1940s. Natural recharge through rainfall would take over 6,000 years to restore a depleted Ogallala. No pipeline, no desalination facility, no other aquifer can substitute for it. The aquifer is finite, and for decades it has been treated as if it were not. USGS data from 2024 shows water table levels in parts of western Kansas and the Texas Panhandle have fallen more than 150 feet since the 1950s. Aquifer levels in parts of western Kansas dropped more than a foot in 2024 alone, with southwest Kansas recording a 1.52-foot decline between January 2024 and January 2025. In West Texas, the High Plains Underground Water Conservation District reported that over 60% of wells surveyed in 2024 had dropped below the pump intake, meaning the pumps can no longer physically reach the water that remains. Researchers at the University of Texas projected in early 2025 that if current pumping rates continue, up to 70% of the Texas Panhandle portion of the aquifer will be unusable within 2 decades. The economic exposure is substantial. Agricultural products from the Ogallala region totaled roughly $35 billion in market value in 2007, and a 2025 Economic Research Service analysis projected a $50 billion drop in regional agricultural output over the next decade if current water use trends hold. That is not a regional inconvenience. That is a structural disruption to American food production. Kansas Governor Laura Kelly has put the timeline in plain terms. Forget making it 75 years down the road. Some parts of western Kansas don't have groundwater enough to last another 25 years. And the human dimension of the Ogallala's decline shows up most sharply in individual farm families, described this way by agricultural reporters covering the Texas High Plains. His granddad dug the well, His dad pumped the well, and now he's going to be the generation that caps the well. 3 generations. 1 aquifer. No plan. Governing the Ogallala is complicated by the legal framework in Texas, which operates under what's called the right of capture doctrine, a rule that lets landowners pump as much groundwater as they want from beneath their own property, with no obligation to coordinate with neighbors or conserve anything. Your neighbor can drain their land. You can drain yours. Nobody has to answer to anyone else. That doctrine makes collective management of a shared, irreplaceable resource nearly impossible, and the policy gap runs national. Despite the Ogallala's importance to American food supply, no overarching federal policy exists to protect it from depletion. Management fragments across 8 states, each with different rules and different political pressures, and the result is a shared resource running out in slow motion. And the Colorado River runs 1,450 miles through 7 states: Colorado, Wyoming, Utah, New Mexico, Nevada, Arizona, and California, and delivers water to roughly 40 million Americans in major cities including Denver, Los Angeles, and Las Vegas, as well as farms that produce food for the entire country. For more than 2 decades, it has been in serious trouble. The modern crisis effectively began around 2000, when a prolonged drought took hold across the American Southwest. Since then, the elevation of Lake Mead, the nation's largest reservoir, backed up behind Hoover Dam, has dropped by approximately 160 feet. In 2021, for the first time in history, the Secretary of the Interior declared an official shortage on the Colorado River, triggering mandatory water cuts for states drawing from it. By the summer of 2022, the driest 23-year stretch in more than a century had sent reservoirs to historic lows, and the Biden administration called for emergency cuts across the basin. Drought intensified the crisis, but the underlying problem predates the drought. The Colorado River Compact, the foundational legal agreement governing water allocation, was written on the assumption that average annual flows were 16.4 million acre-feet per year. Actual measured flows from 1906 through 2024 averaged only about 14.6 million acre-feet. During the most stressed recent years, available flows fell to 12.7 million acre-feet while consumptive use averaged 19.3 million acre-feet, meaning the basin was drawing nearly 7 million more acre-feet per year than the river actually carried. The math was wrong from the beginning, and decades of drought made a pre-existing gap into a full emergency. The groundwater dimension compounds the surface water crisis. Arizona State University researchers found the Colorado River Basin lost about 27.8 million acre-feet of groundwater between 2002 and 2024, roughly equivalent to the entire storage capacity of Lake Mead. The river isn't the only part of the regional water system under stress. As of early 2025, snowpack in the lower Colorado River Basin sat at 23% of the median for that time of year, which suggests limited near-term recovery for the reservoirs that store the river's flow. And now, a political reckoning has become unavoidable. The key operational agreements governing water sharing under the so-called Law of the River expire in 2026. 7 states are negotiating new terms, and federal officials have warned that if those states cannot agree, the U.S. government will impose its own solution. The Department of the Interior has been direct. Every sector in every state has a responsibility to ensure that water is used with maximum efficiency. In order to avoid a catastrophic collapse of the Colorado River system and a future of uncertainty and conflict, water use in the basin must be reduced. Reduced by how much and by whom, that's where the negotiations get brutal. Upper basin states like Colorado, Utah, Wyoming, and New Mexico argue they've already voluntarily cut their use. Lower basin states, particularly California, draw the largest total share, and they face pressure to absorb the deepest cuts. California's agricultural sector uses enormous volumes of Colorado River water, and the politics of asking that sector to pull back are among the most fraught in Western American governance. Cities need water. Farmers need water. Tribal nations hold treaty rights to water. Ecosystems need minimum flows to survive. The Colorado River negotiations will define the American West for the rest of this century, and the clock on reaching a deal is running. Houston dropped 9 feet and lost a neighborhood to the bay. New Orleans spent $15 billion on flood defenses that are themselves subsiding. Airports and subway systems along the East Coast sit on ground that measurements confirm is going down. Arizona's desert floor cracks open in fissures 90 feet deep. California's Central Valley has sunk as much as 28 feet in some locations and continues losing elevation. The Ogallala Aquifer is draining faster than 6,000 years of rainfall can replace. The Colorado River was overallocated the moment the compact was signed, and the bill for that comes due in 2026. What connects all of it is not climate change, though climate change makes every one of these problems worse. What connects them is the long-term extraction of underground resources, water primarily, but also oil and gas, at rates the Earth cannot sustain, in a way that delivers benefits immediately and defers costs to a future that has now arrived. Sediment compacted by groundwater removal doesn't decompress. Storage capacity lost in Houston, in the Central Valley, beneath Phoenix, that's gone. The Ogallala took millions of years to fill. The Colorado's foundational water agreement was built on flow estimates that turned out to be wrong, and no one corrected the math for a century. What can actually be done is a fair question, and the honest answer is less than anyone would like, but more than nothing. The Michoud neighborhood in New Orleans showed that land can partially recover when pumping stops. Houston's Subsidence district demonstrated that regulation can halt the damage even when it can't reverse it. California's SGMA created a legal framework towards sustainability by 2040. Arizona's new active management area designation for the Wilcox Basin brought long unregulated pumping under oversight for the first time. All of those are genuine steps forward. But every one of those interventions arrived after substantial damage had already accumulated. Brownwood was underwater before Houston implemented its regulations. The Frying Kern Canal had already lost 40% of capacity before SGMA passed. Arizona's fissures had been tearing through the landscape for decades before the Wilcox Basin got its first AMA. The pattern holds across every case in this video. The response comes, but it comes late. Leonard Ohenhen, the Virginia Tech researcher who led the most detailed study of American urban subsidence, put the core problem plainly. The problem is not just that the land is sinking. The problem is that the hotspots of sinking land intersect directly with population and infrastructure hubs. 33.8 million Americans live on sinking land in the 28 biggest U.S. cities alone. 40 million people depend on a river running short of the water they were promised. Farms producing a fifth of the nation's food draw from an aquifer with no realistic replacement. The ground beneath the United States has been sending a signal for decades, measured in millimeters and feet and aquifer readings and fissure surveys. The only question left is whether the response comes early enough to change the outcome, or late enough that the only thing left to do is manage the loss. That is the story of why parts of the United States are sinking, cracking, and drying, and it is still being written.